Here we have a rational expression, and the first thing that we're going to look for is we're going to find out what's happening locally at x equals 4 from the x minus 4 factor, and at x equals 1 from the x minus 1 factor. So that x minus 4 factor cancels out. Okay, so what that means is it is a whole at x equals 4. So if I want to find the coordinate of the whole, y coordinate of the whole, I can just plug in the x value. But we're going to do it formally using a limit. So I'm going to use a limit and up here, and I'm going to find the whole using a limit. As x goes to 4, I'm going to plug 4 into my expression. So I get 6 times 4 plus 3 is 27 in the numerator. And in the denominator, I'm going to end up with 4 minus 1, but I'm going to square that, so I get 3 squared. So working that out, 27 over 3 squared gives me my y coordinate of 3. So what that means is my whole is at x equals 4 and y equals 3. So I put that in the table here. I'm also going to draw that in. X equals 4, x equals 4, y equals 3 is going to be a whole at that point. Okay, so I've got my whole. The x minus 1 factor at x equals 1, there's a vertical asymptote. So I'm going to draw in my vertical asymptote here. Okay, so at x equals 1, I have a vertical asymptote. Now, I want to see what's happening at this vertical asymptote. So I'm just going to use a limit, a one-sided limit, and approach the negative or positive 1 value from the negative side. When I do that, I end up with plugging the 1 into the numerator. So I'm going to get 6 plus 3 is positive. And in the denominator, I'm going to approach it from the negative side. Well, that means that I'm going to put like 0.9 in there. That gives me a negative value inside the bracket. So I'm approaching 0 from the negative side. However, that is squared. And because that's squared, that's going to affect the value of that. That's going to be positive. So I'm going to divide by 0 to get infinity, but I'm going to get positive infinity. That means I'm approaching my asymptote from the left, going to positive infinity. And I can do that same thing from the right. As I plug in 1 into the numerator, I get positive 9. In the denominator, I'm going to plug in 1 that's close to 0, close to 1, but on the positive side. That's going to approach 0 from the positive side. Now that I'm going to square that, which doesn't really affect anything. But so I end up with dividing by 0, which is infinity, and checking the signs, it's going to be positive infinity. So in this case here, this is actually approaching the right-hand asymptote going to the positive direction. In fact, they are both pointing up from both sides. And this happens when we have this squared, or a multiplicity of 2 in the denominator. Squared denominators will give this type of feature, going up from both sides. I'm going to look for a 0 here. So the 0 comes from the factor in the numerator. So 6 plus 3, when I solve that equation, I'm going to end up with negative 1 over 2. It's negative 3 over 6, which simplifies to negative 1 over 2. So I have a 0 at negative 1/2. So I'm going to put that 0 in here. So I'm starting to get a few points. Looking for horizontal asymptotes, I'm going to do a limit as we go to infinity. So we have a squared factor in the denominator. So I'm going to be going to 0. I'm going to be going to 0 because I have a bigger power in the denominator. It's basically a weak over strong situation. Now, for the negative infinity, I plug that in. Again, I have weak over strong, so it's going to go to 0. We can actually tell which side of 0 we're coming from. So first of all, I'm just going to draw that in. There's my horizontal asymptote. Okay. Now, we don't need to do this, but we can actually tell which side of 0 we're coming from if we just check the signs. If I take a look at the limit as x goes to negative infinity, that's going to give me a negative in the numerator and a positive in the denominator because the squared factor. And so I'm actually going to approach 0 from the negative side. So I'm actually going to come up to that asymptote here. Okay, and we're going to see that we probably, based on the rest of the graph, that's probably going to be the case anyways. And we could do the same thing for positive infinity. We're going to have positive in the numerator, and the denominator is always positive. So we're going to actually approach the horizontal asymptote 0 from the positive side. And it actually looks like that's the case based on some of the coordinates that we have here. So we have the whole and the vertical asymptote. It does look like that seems consistent. Okay, so that does seem consistent, but we don't really need to analyze that as positive 0, negative 0, because we're going to see that it actually, the rest of the graph will show us that that is in fact the case. Okay, so we need a first derivative here. We want to find a max-min point. So I'm going to differentiate this. So f prime of x, differentiating 6x plus 3 over x minus 1 squared. I'm going to differentiate the numerator. I'm going to leave the denominator as is, minus 6x plus 3, and then differentiate the denominator to 2x minus 1. That's going to be all over x minus 1 squared, so power 4. Now I'm going to make a note here. We should simplify when possible. Because if we do that, we have a common factor of x minus 1 here, here, and here. When we do that, we make the algebra much easier and simpler. We don't have an extra x minus 1 factor to work with. So once I've done that, I'm going to expand out this bracket. So 6x minus 6 minus 2 times 6x is 12x, minus 2 times 3, which is minus 6. And that is my numerator. I should just be careful of my signs though. Okay, just double checking the signs. You should always double check signs when we have lots of terms like this. But I can simplify that into negative 6x minus 12 all over x minus 1. And I'm going to simplify that to factor the negative 6 out. So I get x plus 2 over x minus 1 cubed. Okay, so that means then that this is equal to 0 at x equals negative 2. And so I need to put that into my slope chart. At x equals negative 2, I have a 0 slope. Okay, so I'm going to put that into my table of values. At negative 2, I'm going to calculate a y coordinate. So negative 2 into the expression, I get 2 times 6. Negative 2 times 6 is negative 12. Plus 3 is negative 9 in the numerator. And then negative 2 minus 1 is negative 3 squared. So that works out to be negative 1. So I end up with a coordinate at negative 2, negative 1. Okay, so it looks like it's going to kind of go through here. That looks like it might be a minimum point. Okay, I'm going to sketch that all in later, but that looks like it might be a minimum point. So just maybe kind of looking at what this graph might look like, it looks like it might do this. Okay, and it looks like it might do this. Okay, so that's what we're anticipating the graph to look like. I'm going to check my slopes in my slope chart. So I have to test my derivative on either side of negative 2. So I'm going to check my slope f prime at, let's try negative 3. When I plug negative 3 into there, I'm going to end up with negative 6, negative, and then negative in the denominator. So it looks like it's a negative slope through here. Okay, so it looks like that's the fact that it was a minimum, looks like that's what is showing up in our slope chart. I'm going to plug 0 in. Okay, when x is 0, I'm going to end up with negative 6. I'm going to end up with positive 2. Is that right? Yeah, so I'm going to plug 0. So I'm going to end up with negative in positive and then negative in the denominator, that's going to give me positive slope at x equals 0. So at negative 3, I have negative slope. At 0, I have positive slope. So that looks like it is a local minimum value. Okay, so that is in fact the case. I should really start sketching some of this graph in. So sketching this graph in, this part of the graph, we know we don't have the concavity yet, but we know it's going to go like this. It's going to be a minimum point, go through the 0, and then come up and give an asymptote here. And we know this graph is going to go through the hole, and it's going to follow the asymptote horizontally along 0. So that's pretty much what the graph's going to look like. I'm just going to clean this up a little bit. Oops. I still need to find my inflection point though.